All right, Gen Chem kids, today we are going to talk about bonding, and we're going to talk about the formation of compounds. So instead of talking about individual atoms, we're going to start making molecules. Now, remember, way back from the beginning of the year, we defined what a compound was. So I want to redefine what a compound is. A compound is a pure substance. So basically, I can write a chemical formula for it. So I can write a chemical formula for it because it's a pure substance, but it has two or more atoms in it. Okay, so the other thing we're going to really talk about today is bonding, and we're going to specifically talk about ionic bonding today. There are three main types of bonding today, or three main types of bonding. The first is ionic, and this is what we're going to do today. Ionic bonds are formulas and molecules that are made by putting ions together. Now, ions are charged particles. So if I put a positively charged particle next to a negatively charged particle, we all know that opposites attract. So the attraction between the positively charged particle or ion will attract the negatively charged particle or ion, and it will hold them together, kind of like magnets will hold together. The other type of bonding, we have covalent bonds, and we'll talk about them in about a week or two. Covalent bonds are bonds where we share electrons between two atoms, nuclei. So the electrons can go around both atoms, and because the electrons go around both atoms, the electrons keep those atoms close by each other. And then the third type of bonding is what we call metallic bonding. We will have metal ions in kind of a grid, kind of a crystalline pattern, and the electrons, the valence or the outermost electrons of those metals will kind of free flow through those positive metal ions. And the free flow of those electrons is what makes the metals stay together. Okay, so there are some of our basic definitions here. So let's define ionic compounds right now. So ionic compounds, once again, compound is something that is a pure substance that has two or more atoms, but ionic compounds are pure substances, two or more atoms, but they're made of ions. So a pure substance made of ions. Okay, and usually when we have a pure ionic compound, those ions have to be, we have positive ions and I'm going to put the S in parentheses because we can have one or more positive ions bound to negative ions. And once again, I'm going to put that S in the parentheses because we can have a single negative ion or many negative ions. Okay, so we have positive ions bound to negative ions by electrostatic attraction. Now I want to highlight this word, electrostatic attraction. Now it sounds like a really big, fancy, hard word. It's really not. Electrostatic attraction just means that we have opposite charges. We're going to have positives next to negatives, and because positives attract negatives, those attractions between the opposite charges are going to hold things together. It's kind of like magnets. So I want you to think of ionic compounds as positive ions next to negative ions being held together like magnets. So this is kind of like magnets. Okay, let's define an ion. We haven't really defined ions yet. So an ion is an atom or a group of atoms where the positive or the proton number does not equal the electron number. So basically, it's an atom or group of atoms where the number of protons does not equal the number of electrons. Now remember, protons are positively charged, electrons are negatively charged. So if the proton number does not equal the electron number, that means that atom or that group of atoms has a charge. So ions have charges, or these ions will have a charge. Okay? So the next thing I want to talk about is how these ions are made. So let's change the color again. Now remember, when we deal with an atom in normal chemical reactions, we cannot change the number of protons. Because if I do change the number of protons, I change the element that I have. So the only thing I can really change is the number of electrons, okay? And I want you to remember that electrons are negative, okay? So if I want to make a positive ion and I can only change the number of electrons, how do I get something to be positive? Do I add more negatives or do I take negatives away? You're right, I take negatives away. So positive ions are made by losing electrons. Okay? So I will take that atom and I will take electrons away. I will lose electrons. So if that's how I make positive ions, how would I make negative ions? You're right. I make them by gain. I gain electrons, or I put more electrons on that atom or on that group of atoms. So losing electrons gives me a positive ion. Gaining or putting more electrons on it, an atom or a group of atoms, gives me a negative ion. Okay, so very first thing I want to do on learning about these is we want to start drawing the dot pictures of potassium. So let's look at our periodic table. We're going to look at potassium. It's right here. So potassium is in that very first column, so we can say it has how many valence electrons? Did you say 1? Yes, potassium has 1 valence electron. So if it has 1 valence electrons, the dot picture I'm going to do is going to be potassium with 1 dot. Now my next question is potassium stable? Now by stable, let's define what I mean by stable. Does it have a noble gas configuration? And remember, a noble gas configuration is going to have all 8 dots with it. The only exception to that would be helium with 2 dots. Does potassium have all 8 valence electrons around it? No, so it is not stable. Potassium does not have an octet. Now remember that noble gas configuration is an octet. We want 8 valence electrons. So let's draw fluorine really quick. Let's look at fluorine first, actually. Let's grab the periodic table. So fluorine's up here. It is in group 17. So being in group 17, we know that fluorine has how many valence electrons? 7. Did you say 7? I hope you did, because if you did, you're right. All right, let's change the color here. So fluorine will have 7 valence electrons, which gives us 7 electrons in the dot picture. Is fluorine stable? In other words, does it have an octet? Does it have a noble gas configuration? No. It's missing 1. It needs 1 more electron. It has 7 valence electrons, not 8. Okay, so let's look at this next thing. Now, if I draw potassium plus, notice that plus tells me I have a charge of +1. That means I have removed how many electrons? 1, because -1 being taken away, minus -1 is actually +1, right? So that will give me a positive charge. So I'm going to take this valence electron and I'm going to get rid of it, okay? So if I get rid of potassium's valence shell, that means, let's look at the periodic table. If I get rid of that 1 electron, I go back to argon's noble gas configuration. So potassium +1 is going to be the essentially 0 valence electrons on the outer shell, but that next shell, I'm going to have all 8 electrons, just like argon. So the way we would write this would be potassium plus would be like this. Okay? They're the same. So the question is this stable? Yes, this is stable. This is stable because I have an octet. Okay, let's look at fluorine. Now, fluorine, here we go. We've got a -1 here. So if I have a -1, that means I've added an extra electron. So let's look at what will happen if I add an extra electron to this. What is this going to look like if I add an extra electron? Is fluorine now going to have 8 valence electrons with that -1 charge? I've added that extra electron right there. So my question is it stable like that? Yes. This has an octet. Now remember, octets mean 8 valence electrons. Okay? So when we create ions, we are always trying to create octets. We will either lose electrons or we will gain electrons to create that stable octet or that noble gas configuration. So here's a big idea for today. One of the few big ideas that we have. Big idea. Metals. All metals tend to lose electrons. Okay, metals tend to lose electrons to form positive ions. So metals are going to be positive. Okay, and nonmetals tend to, oh boy. Why did it just do that? nonmetals tend to gain electrons to form negative ions. Okay? So metals create positive ions and nonmetals create negative ions. Now, I want to show you on the periodic table how we can assign charges to a fairly decent amount of these elements on the periodic table. So let's spend some time on the periodic table now. I'm going to move this up here. Now, let's think about these as groups. So group 1, how many valence electrons do we have in group 1? Hopefully you said 1. So remember, we want to have an octet. So there are 2 ways that we can get to have an octet. We can either get rid of that 1 valence electron, or we can gain 7 valence electrons to get to the octet. So which do you think is easier, to lose 1 or to gain 7? I think losing 1 is a lot easier. So if I lose an electron, I'm going to have a +1 charge. So what we can say is all of the group 1, let's highlight this, all of the group 1 elements, these guys will all, when they make ions, acquire a +1 charge. So I'm going to put +1 up here. Now let's look at group 2. How many valence electrons do group 2 elements have? Hopefully you said 2. So not an octet. So how do we get to an octet? We have 2 options. We can lose 2 electrons, or we can gain 6. Which do you think is easier, losing 2 or gaining 6? Hopefully you said losing 2. So if I lose 2 electrons, these guys are going to all have a +2 charge. So let's highlight this. Let's do green. Okay, these guys can all have a +2 charge. Now, these here in the middle, the transition metals, they can have multiple charges. So we're not going to tackle them right now. There are a few, though, that do have set charges. So let's tackle the few that do have set charges. So silver right here always has a +1 charge. Cadmium right here always has a +2 charge. Zinc always has a +2 charge. And aluminum always has a +3 charge. Aluminum always has +3. Okay? So another thing I want to do really quick, I want to put in the line between the metals and the nonmetals. So I'm going to put that in really quick. Make that really thick. We're going to start talking about the nonmetals. Actually, let's make it like this. Okay, let's get another highlighter color. Let's talk about the halogens really quick. So the halogens are this group right here. How many valence electrons do they have? Hopefully you said 7. Okay, these guys have 7. So if they have 7 valence electrons, how can they get to 8? There are 2 ways that they can get to 8. They could lose all 7 of their valence electrons, or they can gain 1 more. which one is going to be easier? Losing 7 or gaining 1 more? Hopefully you said gaining 1 more. So if you gain an extra electron, you're going to have a -1 charge. So the halogens will all have a -1 charge. Let's talk about group 16, and this only goes for the nonmetals in group 16. How many valence electrons do they have? Hopefully you said 6. Okay, so that gives us 2 options to get to our 8. We can lose 6 electrons, or we can gain 2. Which do you think is easier? Hopefully you said gaining 2. Gaining 2 electrons is a lot easier than losing 6. So if I gain 2 electrons, these guys are going to have a -2 charge. So let's highlight the ones that will acquire a -2 charge. Let's see, let's choose yet another color. Now you'll notice that I am not going to do this whole column because we do have the metals coming in, and tellurium right here at the bottom is actually not considered a nonmetal, it's a metalloid. So it is not going to be part of this group. Let's talk about group 15. How many valence electrons does group 15 have? Hopefully you said 5. So that gives us 2 options to get to a noble gas configuration. So if I have 5 valence electrons, I can either lose those 5 valence electrons, or I can gain 3 more. Which do you think is easier, 5 or 3? I think 3 is more easily done. So if I gain 3 electrons, I will have a -3 charge. So these guys, just nitrogen and phosphorus, will acquire a -3 charge because arsenic is a metalloid. So we're not really going to count them. Now remember, the noble gases here, they have full valence electron shells. So they're not going to give up electrons to create an ion at all. So these are the electrons and ions that you are going to very easily be able to pull out of the periodic table. I need you to know these patterns. So if you want to, grab an extra periodic table and color it up like this so that you have this reference. Okay? All right. So let's go back to this. We're going to do the dot picture for calcium. So if I look at this periodic table, calcium is right here. So calcium right next to potassium, it has 2 valence electrons. So if calcium has 2 valence electrons, I'm going to draw those 2 valence electrons. So in order to achieve a noble gas configuration, I can lose those 2 electrons or I can gain 6 more. I think losing 2 electrons is a lot easier. So I'm going to create a +2 charge. Now, if I create that +2 charge and lose those 2 electrons, I go back to the noble gas configuration of argon. Okay? So it's essentially calcium is going to be this, calcium +2 is going to be the same as argon. They are electron-wise the same. Now remember, calcium is going to have 2 more protons. Okay? So calcium will have 20 protons. Argon will have 18 protons. But they will both have 18 electrons. Okay? So electron-wise, they are going to be the same. All right. Let's do some more. I want to do the dot picture for bromine. So let's look at bromine. Bromine is right here. So it's in the halogen. So it has 7 valence electrons. So let's draw bromine. So we have 7 valence electrons. So we have 2 options to get to that noble gas configuration. We can lose 7 electrons or we can gain 1 more. And I would say that gaining 1 more and having a negative charge is a lot easier. So if I gain 1 more electron, I'm going to put that extra electron right there. So we will have bromine. And notice with the charges, I put brackets around it with the charge. So that essentially, if I gain that extra electron, bromine becomes electron-wise like krypton. So it's going to electron-wise be the same as krypton. Now, that means that we are going to have 36 electrons, or not valence electrons, just electrons, and 36 electrons here, but 35 protons here and 36 protons here. So electron-wise, they are going to be the same. Okay? So let's look at how we put these things together. Now, remember when we put ions together, the sum of the charges has to be equal to 0. So to make, oh, I love how the color changed. To make ionic compounds, the sum of all ionic charges has to be 0. We don't want the compound to have a charge. Compounds have no charge. So what we have to do then is to find, and this is going to sound like 5th grade math, we have to find the least common multiple between, that has 2 ends, the 2 ions charges. Do you remember back in 5th grade math finding the least common multiple between things? We're going to do that again. Okay, so let's look at potassium, and we're going to look at fluorine and determine the charges that they acquire. So potassium is right here. It is going to be a positive 1. Fluorine is right here. It is going to be a negative 1. So let's write those here. Let's change color again. So potassium is a positive 1. Fluorine is a negative 1. Now, what are the multiples of 1? Least common multiple. 1 times 1 is 1, 2, 3, and so on, right? Because it's the identity property of multiplying by 1. So both of them have charges of 1. So our least common multiple is 1. So we want an overall charge on the positive side of plus 1 and our overall charge on the negative side of negative 1. So to do that, I need 1 potassium to get to a positive 1, and I need 1 fluorine to get to a charge of negative 1. Okay? So the other thing that we also need to remember is we always write, let's do this in a different color. We always write the metal first. Okay? The metal always comes first and the non-metal comes second. Always, always, always. Okay? So when we write potassium and fluorine, we're going to write 1 potassium and 1 fluorine. That is how we would write that compound. Now to figure out how we would name it, every time we name something, we name the metal, And then we do the root word of the nonmetal, and we add the suffix "ide." So we would call this potassium fluoride. Let's write this over here. Potassium fluoride. Okay, so that is how we would name this. All right, let's go on to calcium and fluorine. Now we've already talked about fluorine. Okay, I want to change the color here. So fluorine, we've already determined would be -1. Okay, let's look at calcium. Oops. Calcium, right here, it's in our +2 column. So calcium is going to be a +2. Now, we need to find our least common multiple. So let's list multiples of 2. So 2 times 1 is 2, 4, 6, 8, and so on. So if I have a -1, my multiples of 1 are 1, 2, 3, 4, and so on. What's the first one that matches? The first one that matches is 2. So I know I have to have a charge of +2, and I have to have a charge of -2 to get it to match. Okay, so how many +2s do I need to get a charge of +2? Hopefully you said 1. And how many -1s do I need to get a charge of -2? Hopefully you said 2. So I'm going to need 1 calcium for every 2 fluorines. So 1 calcium, 2 fluorines. Notice I make that 2 by a subscript. So I do numbers with subscripts. Now to name this, remember we name the metal and then we do the root word of the nonmetal. Okay, so the metal here is calcium and the nonmetal is fluorine. So the root of fluorine is fluor. And then we're going to add on the suffix "ide," calcium fluoride. Okay, let's look at another one. So we have calcium, which we've already determined is a +2. And then bromine. Let's look at bromine. Bromine is right here. It's a -1. So bromine is a -1. Now we want to once again find our least common multiples. So our multiples of 2 are 2, 4, 6, 8, right? And our multiples of 1 are 1, 2, 3, 4. So once again, we're going to match at 2. So how many calciums do I have to have a +2 charge? I need 1 calcium. And how many fluorines do I have to have a -2 charge? I need 2 -1s. So I'm going to need 2 fluorines. So when I write this formula, the metal comes first. I need 1 of them. I need 2 fluorines. Oh, I said bromine. Sorry. Bromine is a -1. I get it. So we're going to need 2 bromines. So when I do that, we're going to have calcium bromine bromide. Okay, I want you to take a minute and see if you can figure out potassium and bromine by yourself. Okay, you ready to check? All right, potassium. If you looked on the periodic table, potassium is in this very first column, so it is a +1. And bromine is right here, so it is a -1. Okay, what is the least common multiple between +1 and -1? Hopefully you said 1. So that means I need 1 potassium to get to a +1, and I need 1 bromine to get to a -1. So when I write this, I'm going to write the metal first.